Welcome to TRL, the second lecture on vectors. In this lecture, we're going to look at vectors in 2-dimensional and 3-dimensional systems, addition of vectors, subtraction of vectors, vector multiplication by a scalar, and then at the addition of vectors, we're going to look at the triangle law of vector addition, the parallelogram law of addition. Now let's first look at vectors in 2-dimensional systems. When we talk about the 2-dimensional systems, we're simply talking about the OXY plane or the Euclidean plane. That is, having the x-axis and the y-axis. In geometry, any vector in the 2-dimensional system can be expressed as the vector r equals xy, which also equals xi plus yj, where I and j are unit vectors along the x and the y axis respectively. As an example, assuming you have a point T in the 2-dimensional system with coordinate 3, 4, the vector OT of the vector r can be expressed as vector OT equals vector r equals 3, 4 equals 3i plus 4j. Note that 3i and 4j are called the perpendicular components of vector r. The scalars 3 and 4 are called the components of r in the direction of the x-axis and y-axis. The dotted pair 3, 4 is known to be the coordinate of t, and the magnitude or modulus of r or vector OT is given by the magnitude of vector r equals 4 square plus 3 square, all square roots, which equals the square root of 25, which equals 5. Now we know from elementary that the magnitude of a vector is given as the square root of open bracket x2 minus x1 all squared plus y2 minus y1 all squared. So in this case, the x2, the x1 and y1 is 0, 0. So we have 3 minus 0 all squared, which is 3 squared, and 4 minus 0 all squared, which is 4 squared, giving me the root of 25, which equals 5. Now we represent vectors in this particular form to make addition of 2 or more vectors very simple and clear. Now looking at the vectors in the 3-dimensional systems, the 3-dimensional system deals with the 3 axes, that is the x-axis, the y-axis, and the z-axis. Now let P be a point in the 3-dimensional system. This means that P is going to have coordinate x, y, and z. The vector OP or the vector r can be represented as vector OP equals vector r, which equals xi plus yj plus zk, where I, j, and k are unit vectors along the x, y, and z axis respectively. This equals xyz. Then we have that P is going to have coordinates x, y, and z. Now xi, yj, and zk are called the right-angled components of r. The scalars x, y, and z are called the component or resolved part of r in the direction of the x-axis, y-axis, and z-axis. The other triplet x, y, z is known to be the coordinate of P. The magnitude or modulus of vector r is given as the modulus of r equals s squared plus y squared plus z squared all square roots. This is because having this vector OP, the initial point is the origin, which has coordinates 0, 0, 0. So we have P having coordinate x, y, z So we have x minus 0 all squared giving me x squared, y minus 0 all squared giving me y squared, plus z minus 0 all squared giving me z squared, all square root. Addition of vectors. Let's look at the triangular law of addition. Given two vectors as the consecutive sides of a triangle, AB, vector AB and vector BC, the sum of these two vectors is represented by the third side of the triangle, that is vector AC. That is vector AB plus vector BC equals vector AC, and that is to say that for we to move from point A to point C, we can go through point B to point C, that is moving along the path of vector AB and vector BC. So you can either go in this particular direction, which also equals going in this direction first and going in the other direction second. Now if vector AB equals vector A and vector BC equals vector B, then vector AC equals vector A plus B, because moving in this path is A and then moving in this path is B. This means that going along this path is simply A plus B. Now it is very important to note that the terminal point of vector A is the initial point of vector B. It is very important to note this under the triangular law of addition, that always the terminal point of vector A is the same as the initial point of vector B. It's very important in this section. Note that AC is a direct line segment joining the initial point of A and the terminal point of B. Now we look at the parallelogram law of addition. If two co-initial vectors, vector OA and vector OB, are given to represent the two adjacent sides of a parallelogram, then their sum is represented by the diagonal of the parallelogram whose initial point is the same as the initial point of the given co-initial vectors. Thus, vector OA plus vector OB equals vector OC. Vector OA plus vector OB equals vector OC. It is very important to note that under the parallelogram law of vector addition, OB and OA have the same initial point, whereas in the triangular law of vector addition, vector OA and vector OC do not have the same initial point. That is, the terminal point of vector OA will be the initial point of vector AC. Now, we get this particular instinct from the fact that since this is a parallelogram, then vector OA is parallel to vector BC and vector OB is parallel to vector AC. So if OB is parallel to vector AC, then this particular side alone of the parallelogram gives us the triangular law of addition, because the terminal point of vector OA, which is A, becomes the initial point of vector AC, which is A. So in this case, we have that OC equals vector OA plus vector AC. However, in this case, vector AC is parallel to vector OB. So we can have OA plus OB equals vector OC. Now, if vector OA equals vector A and vector OB equals vector B and vector OC equals vector C, then we have that vector C equals vector A plus vector B. Right from here, that if vector OA is vector A and vector OB is vector B, we have that vector OC equals vector OA plus OB, in this case giving us A plus B equals vector C. Now let's look at the subtraction of vectors. The subtraction of a vector B from another vector A is defined as the addition of the additive inverse of vector B, that is minus vector B, to vector A. That is, if vector A and vector B are two vectors, then their subtraction is clearly defined as vector A minus vector B equals vector A plus minus vector B, where minus vector B is additive inverse of B. Note that since minus vector B is the negative inverse of vector B, they both have the same magnitude. Now, vector A minus vector B can also be written as vector A plus minus vector B. In this case, minus vector B becomes the additive inverse of a positive vector B. Now, since this is the additive inverse of this particular vector, both vectors will have the same magnitude. However, this particular one will move in the opposite direction of this, since this becomes the minus of this vector. Look at vector multiplication by a scalar. Given a non-zero vector A and a scalar m, the scalar multiple of the vector A by m is denoted by m vector A. Now, m vector A is a vector whose magnitude is m times that of A and whose direction is the same as that of A. Now, in the case where m is positive, multiplying the scalar m by the vector A gives us another vector whose magnitude will be larger than that of vector A, but will have the same direction. However, if m is negative, it changes the entire vector result that we will get by multiplying the negative scalar by the vector, giving us a different magnitude and a different direction. Now, if vector A is denoted by xi hat plus yj hat plus zk hat, then the vector multiplication by the scalar m is giving us mx I hat plus my j hat plus mz k hat. Now, we use a hat to represent a unit vector. So in this case, I hat is a unit vector along the x-axis, j hat is a unit vector along the y-axis, and then k hat is a unit vector along the k-axis. In this lecture, we've looked at representation of vectors in 2D and 3D systems, the addition of vectors, the subtraction of vectors, and vector multiplication by a scalar. And under the addition of vectors, we've looked at the triangle law of addition and the parallelogram law of addition. In our next lecture, we're going to look at the ratio theorem, that is the internal division and external division of the magnitude between 2 points.